an oxidizing agent in one compartment that pulls electrons through the wire from a reducing agent in the other compartment. The cell potential or pull or driving force on the electrons is also called the electromotive force or EMF. All right, so now we're going to need to define a couple of terms about that. So one is voltage and the other is current. Voltage is the difference in potential energy between the reactants and the products. It is called the potential difference. The unit is going to be the volt. Current, on the other hand, is the number of electrons that flow through a system per second. So if you think about this in terms of plumbing, voltage is like the pressure, your water pressure, and current is going to be like your flow rate. Right? My pressure is 150 psi, and I'm getting out 1 gallon per minute. The units on current is the amp. If you have to take a choice between 1,000 volts and 1,000 amps, pro tip, take the volts. Right? The potential difference is not the same thing as the current flow. And it is way more damaging to get current flow than it is to get potential difference. So if I drop a penny off the top of the Empire State Building, it had a lot of potential energy, but I'm probably going to go, that hurt. Whereas getting hit by a freight train that is going very slowly and is moving a lot of mass is still going to hurt a lot. 1 volt is equal 1 joule of energy per coulomb of charge. So coulomb is our fundamental unit of charge. The voltage needed to drive the electrons through the external circuit. Right? And a voltage is always going to be a difference in potential. So see this word difference? This is a key word in here. Right? So what's the difference in the potential chemical energy? Which, if it's a difference, implies that you always have to have 2 points in it. Right? What is the voltage of one thing relative to another? What is the potential energy difference of the penny on my head versus the penny on the Empire State Building? Right? So I'm always going to need to make that measurement from 2 points. That's why you got 2 electrical leads on your voltmeter. Right? An amp of current is 1 coulomb of charge flowing through each second. So 1 amp is 6.242 times 10 to the 18 electrons per second. So about half a mole of electrons. The voltage is the amount of force pushing the electrons through a wire. It's called the EMF. And the electrode's surface area is going to, on the current side, dictate the number of electrons that can flow. Larger batteries can produce larger currents. They're going to have the same potential. So if I pick up a AA battery, it's like 1.5 volts. If I pick up a AAA battery, it's going to be 1.5 volts. If I pick up one of those honking big D-cell batteries, still going to be 1.5 volts because the chemistry involved is the same. And so the potential or the voltage is the same, but my current capacity or the length of that battery's life might be different. Okay? So what does voltage mean? We're going to lay down some of these other terms for us. The coulomb is the fundamental unit of electrical charge. 1 electron has 1.602 times 10 to the minus 19 coulombs of electrical charge. A Faraday is the charge on 1 mole's worth of electrons, which we're going to see is going to be more useful for us as chemistry people. So 1 Faraday is going to be 1.602 times 10 to the minus 19 coulombs times Avogadro's number, or 96,484 coulombs per mole. The current is the movement of charge. We're using I because we're chemists, not engineers. It's the movement of charge of electrons in a circuit. 1 amp is 1 coulomb per second. We have a term called resistance, and that's the opposition to current flow, and the units for that are in ohms. And we've got voltage, or E-cell voltage. That's the electrical potential difference between 2 points in a circuit, resulting from the amount of work required to move an electrical charge between those 2 points. So 1 volt is 1 joule per coulomb. And so these are the dudes who are behind that. Charles Augustin de Coulomb was June 14, 1736 to August 23, 1806. He's a French physicist known for the discovery of Coulomb's law. Coulomb's law, remember, that's the thing. That's where you've got what is my energy, and it's going to be related to the charge of the first particle and the charge of the second particle and the inverse square of the distance. Right? So that's that charge that says y is the lattice strength for sodium fluoride bigger than it is for sodium chloride? Or why does HF act like a weak acid when HI is going to be a strong acid? Right, so that charge separation and charge magnitude, right? That's Coulomb's law. Really, really important for when you're talking about what are the energies involved in things with electrical charges. And if you're in chemistry, right, all of Gen Chem 1 was about electrons, and now we're talking about energy, so he's going to be kind of important in some of those relationships. Michael Faraday, on the other hand, like I said, certified badass, one of the first people to really get into experimental chemistry. He was an empirical scientist, did a lot of experiments, kind of a self-taught, self-made man. He kind of grew up poor and worked as a demonstrator and did experiments as somebody's, hi Michael, go machine me a bunch of screws so I can do this experiment. And really, people were like, oh man, this guy's good. And he was really good. So he's a fellow of the Royal Society, 1791 to August. Died August 25, 1865, English chemist and physicist, or natural philosopher, that was the terminology at the time, contributed to the fields of electromagnetism, electrochemistry. He was one of the first guys to actually synthesize nanoparticles, right? These are nanoparticles of gold. So using a method very similar to the method that I used to make gold nanoparticles in my research when I was doing my PhD. And these things are still around. You can go to a museum and see them. So they've been there since like the 1800s. He was also the guy who developed the Faraday cage. So here's somebody getting zapped by a giant Tesla coil, and they're perfectly safe because they're inside that Tesla cage. It's why your car is a safe place to be in a rainstorm when there's lightning. It's not because the rubber tires are insulators. It's because the electricity in the lightning bolt is going to go around you because you've got a metal car body and the electrons are going to follow that path of least resistance. Important note, voltage is always, always, always a difference. Therefore, any voltage measurement needs a reference point known as a known point or a defined potential, usually zero. So what is the most common reference point when you say, I'm looking at an AC wall output and it's 120 volts? What is the reference? It is ground or earth. And what is the reference point in the measurement from our voltaic cell when we're measuring, say, from a silver lead to a black lead that's attached to copper? Well, that's going to be 0.46 volts. So we're making a measurement of our anode relative to our cathode. All right, so we're making a AG relative to copper measurement. We've got some ways to measure our potential. It's a voltmeter. It works by drawing current through a known resistance, and a potentiometer, which is a variable voltage device, which is powered from an external source and connected in opposition to the cell potential. And it's going to determine the maximum potential by doing the measurement under conditions of zero current so that no energy is wasted. So two slightly different ways of measuring things. You will oftentimes see people use those interchangeably. Not much I can do about that, but they're just two different, slightly different terms. The voltage in that is going to be adjusted until, in a potentiometer is going to be adjusted until no current flows, and then the cell potential is equal to the magnitude and opposite in sign and the voltage setting of the potentiometer. So the value represents the maximum cell potential since no energy is wasted in heating the wire. So your potentiometer is going to be a little bit more accurate. It's a little harder to implement, and they're a little bit more sensitive. People are just going to use voltmeters. You can go pick one up at like Walmart for $5, and it will do the job just fine for most things. So let's do another quick clicker question. What is the reducing agent in the following cell? Where we've got a nickel anode with nickel 2+ in solution, and a salt bridge, and Ag plus silver ions in solution, and a silver cathode. Pause. Okay, it's going to be the nickel. That is the reducing agent because it is the one that is getting oxidized.